Hello everyone and welcome to our next session of our Digital V-Days. I'm very happy to welcome all of you, and so let's dive into our next topic, how to solder components on PCB by using through-hole reflow process. I'm also very happy to welcome Vamsi Gajula, who will do the presentation today and also answer all your questions at the end of our presentation. So if you have any questions, then just put them into the chat and we will answer them at the end of our session. And if there are any questions left after the webinar, then just email us. So then that's, I think, for the start, everything from my side. I wish you an exciting webinar and enjoy it.
Hi, this is Vamsi Krishman. I'm working as a senior FAE for ICANN India, and I've been in the company almost 14 years. Today's topic for Digital Day is THR, that is through-hole reflow. So we discuss about what is through-hole reflow, about the how it is came into the project. The agenda mainly consists of emergence of THR, like how the through-hole reflow has been came into existing in the market. And once we discuss about the emergence, then we also discuss about do we need any requirements designing in the product and the selection of its base materials. And then most importantly, we'll also discuss about the layout and stencil suggestion, like how do you design the layout for the THR process, and what is the stencils. We have a different stencil suggestions available depending upon the application which we are working. And then we have process and the stages of the processing, like when we talk about the through-hole reflow. So we have different stages in there, and we also discuss about the what is going to happen in different stages. And then we also look into the quality requirement of once we assemble the component on the PCB, what quality we need to check so that the after assembling the component has been done properly assembled on the PCB or not. So that we will check it as per the IPC A-610. And then we also discuss about the advantage of through-hole reflows. What are the different advantages we have and how it is going to benefit in the market. And then we summarize what we have discussed, entire thing. And then, of course, if you have any questions, obviously, we also discuss at the end of the presentation. So the first we'll talk about the emergence of two-hole reflow. So first, when the evolution of electronic market came into the picture, so it started with the through-hole components, like we take the through-hole component and we assemble the component on the PCB with the press fitted, and by doing the wave soldering, so we assemble the component on the PCBs. So if you observe in a through-hole component or wave soldering process, we use only one side of the PCB and the components used to be bulk. So as market is evaluated and the more technology came into the picture, we have come up with the small components on the picture, and density of the on the component, on the PCB component, has been increased. So that the assembly component product came into the picture. So where we can assemble the component with the reflow process, and the most importantly, we can use the PCB on the both the sides, like of top side and the bottom side, unless this was not available in the wave soldering process. So but when we talk about this one, the thermal stress came into the picture. What is that exactly means? When you have a PCB where if you have a combination of through-hole components as well as assembly components, and what we have to do is first we assemble the assembly components and then we have to assemble the through-hole components, because assembly components will be assembled at the temperature will be required around the 265 degrees to 285 degrees. When it comes to the wave soldering, the component will get assembled around the 235 degrees. Since we have this huge temperature difference, so we have to assemble the first assembly components and then we have to go for the through-hole components. So what happens here is in assembly components, I think on the PCBs, you have a very small components like capacitors and chip bit ferrites, these things where that has to go a lot of thermal stress. That means when you are assembling reflow, it has to go 265 to 285 degrees. Again, when you are doing the reflow wave soldering process, that product has to go again high temperature like 235 degrees. So doing this, so the small components on the PCBs has to go a lot of thermal stress. Sometimes this may degrade the effect or performance of the components. So in order to overcome this, we have come up with a new technology called through-hole reflow. So where the through-hole components as well as assembly components assembled at a time, so that you can reduce the thermal stress on the components that not affect the performance of the components. And the second thing is the most important thing, you reduce the process. By reducing the process, you will reduce the cost, overall cost of the production process and the components. So we will discuss more on the through-hole, like what kind of requirement of the product is required. So the what has to be changed. So when you consider the through-hole reflow product, the first question comes into the what kind of products do we need to change with respect to of design. So for example, if you look at into this picture, the left hand side, it is a terminal block through-hole component, and the right hand side you can see that is a terminal block which can support the THR, through-hole reflow process. What could you observe here? So when you observe clearly, you can see there is a small change in materials which we have used for the THR process components, and the design also. You can see there is a small design there changing the components. What are this one? When it comes to the material, yes, there is a different material we have used for the housing as well as the contact, and the housing's design also, there is a small dimension change, and some of the additional features also we added in the THR components. The first we talk about the materials which we have changed. So any through-hole component, if you consider if you talk about the connectors, and if you see the data sheet of our product, the first line will be the materials what we have used. So any through-hole component, the plastics which we have used, I mean you can say typically polymers, is PA66 or PBT or PA97, whose temperature competence is a little bit less when you consider with the reflow process. Like this is more or less is like temperature moisture friendly. That means when you expose this material with the high temperature like 265 degrees, the moisture which is there in the polymer will be bulge out, and you can see the blisters on the surface of the connectors. You can see the bubbles, you can say. So this will degrade the component performance. That's the reason this material is not suitable when you're talking about the THR part, this one. So other major limitations when it comes to the material wise about this one, like PA66 and the PBT, the temperature, operating temperature things. If you, as we know that in the reflow process, the temperature will exceed 260 plus, between 260 to 285. So these polymer characteristics are not defined to expose that kind of temperature. If you expose that kind of temperature, you can see there is a melting of the component. So what best material we need to consider? So when you consider for the through-hole THR part, the polymers which we use will be the LCP, liquid crystalline polymer. The reason why we have used for the LCP is the LCP characteristics has high temperature resistance. It can withstand up to 285 degrees, and most of the assembly components which the core material, the plastic material, will be the LCP, and the no deformation. Like even if you expose the high temperature, high moisture, they will not be seen any deformation like between the parts. And the most important thing, the moisture sensitivity level is 1. And another characteristics which LCP has is the thermal coefficient temperature efficiency constant, thermal coefficient constant. That means even if you expose to the high thermal, it will not deform its characteristics. So that's about the materials which we talk about this now. So now we'll talk about there is any change in the design. So as again, if you see this product again, the left hand side we have there is a product of normal terminal blocks which supports the wave soldering, and the right hand side you can see again the THR part. So if you closely observe, there is a small design on the surface of the plastic enclosures. So what exactly if you do? Apart from that, there is some design change of the plastic pegs also. We can see on the bottom. So if you have a close look, you can see the first thing is when you talk about the housings, right hand side, the enclosure size, you can see here exactly there some plastic standoffs has been designed. So why it has been designed is when you place through a THR component on the surface of the PCB, it will allow the solder paste process, I mean reflow soldering process, I mean you can say through hole reflow process very smoothly, and air also can pass easily without creating any bubbles. And second point, if you see this one, there is one more plastic pegs is there between the pins of the connector. So this will also allows the connector should not touch on the PCBs, so that the reason why is if you have any heat waves, I mean high waves, heat waves or temperature wave will be allows freely move on the what you call this gap. And the second thing is what you call solder paste will not deposit under the component. This is very, very important. If you any solder paste is deposited on the ground, that means the soldering has not done properly. So this is about the design considerations we can have. So to make it very clearly that big components, the air force can be as shown in the arrows, the air flows can be done very flawlessly between the housings and the plastic plugs. So if you look out for any THR component which carries very high current, like if it comes to the Worth Electronics, we have up to 57 amps terminal 57 amps where terminal blocks can carry. So that is all made with the THR process, where the waves can be pass easily on the surface of the components. And the same thing, we have another components which can carry very high current applications up to 85 amps also. We have this kind of plastic plugs is available here. So you can see the pins of the connector, there is some kind of standoffs is there. So this will allows thermal heat, I mean you can thermal efficiency, by allowing the air to pass on these things, we can thermal coefficients or whatever the thermal stress can be avoided. So this is about the till now we have seen the designing change with respect to of materials and the what you call the housing. So now we discuss about the pins. So the first question is, do we need to customize the length of the pin? If you ask me, no, but yes, if you see the picture now, it's the pin of the connector is very, very small. So if you do that and if you assemble this component on the PCB, what exactly happens is it will not solder properly, and it will not have a proper mechanical stability as you expect from the through hole components. And then with two short pin, the mechanical stability will be, and it will be like floating on the surface of the PCBs. Like it will be what you call it will not assemble the component as per the standards which we'll talk about. The standards which we're talking about is IPC A-610. So if you assemble the component and the solder paste, it has to be properly assembled on the component, and it has to meet the standards of IPC 610 actually. And second thing is, what is the IP61A standards in the market? So if it comes to that, just give the brief. I will not discuss in detail about this standards. I just give we have three classes normally divided in the market. Depending upon the applications which you are working, you can select that particular class and define yourself. So coming back to the pin construction. So what happens if you have a pin is too long? So when you have a pin is too long and assemble the component on the surface of the PCB, so the pin, the PTH, that penetrated through hole, the pin will eject the solder paste, and once you assemble the component, you can see the solder paste is accumulated on the surface of the PCBs. So again, this will not, by doing this one, this will not give the proper soldering of the component on the PCBs, and it will also create the solder balls could be created on the bottom of the PCBs. So what could be the ideal length? So when you talk about the Worth Electronics, we normally maintain the 2.6 mm pin length. So this pin, if you talk about 2.1 length, so that it can support the pin PCB thickness from 1.6 to 2.3. This is ideal thickness for the THR process. Normally in the market, whenever you are working for the two-hole component, we normally define the PCB thickness should be 1.6 mm to 2.3. So Worth Electronics will maintain maintain 2.6 mm of the connector pin length so that it can support 1.6 to 2.3 mm PCB length. So this is about the, what you call we discussed about with respect to basic materials and the contact designing. So now the most important thing is the second thing is the layout and stencil design. So how do we design the layout and what are the process we need to follow? Do we have anything? Yes, we need to consider the different layout stencil considerations that we need to have some formulas. This one, so this is the PCB thickness, PCB layout, I can say. This is a formula. Normally when calculation the formula VCB means pi dh h square by 4. So where the TB is the PCB thickness, which we discuss normally is 1.6 to 2.3, and the DH is the whole diameter, which you can see bottom of the PCB, and the DSP is the solder paste pad diameters. So and the TB is again if you have this one. So these values you can get it because you are the designer. You can calculate how much you want for this one. Based on that, we can calculate. So if you see in the market, we have two things like rounded pin and the square pin. So if you are talking about rounded pin, we have to take it something else which we discuss in the coming slides. The second thing is how do you calculate the volume calculation of the pin? Again, so we have the formula like V pin pi square, pi into pin radius square into pin into PCB thickness. So PCB pin volumes and the free volumes, and we have some formulas. So for the rounded pin, you need to consider the WP by 2, and the for square pins, you need to consider the A minus B by pi root square. So A this is the distance between A and B. This normally you will get it in the data sheet of the connector, whichever the product you are using. And other thing is volume calculation of the fillet with the purpose guide. Fillet means normally this is the what which we talk about the fillets. Normally this is has to be filled to get the proper soldering process. The V fillet is the formula 0.215 into C square and bracket 0.2334 into C plus pin radius into 2 pi. So what is the pin radius and the pin volumes is exactly given here. So how do you calculate the C value? C is the solder pad diameter minus pin diameter. So solder pad diameter is like this, and the pin diameter comes like from this one actually, divided by 2. And then for the round pin, we have to go for WP for 2, like how discussed. And for rectangular pin, so previously we talk about A minus B. Now we have to, when you are coming for the layout stencil suggestion, we need to do A cross B by pi. So then calculation of solder paste volume and the stencil opening. So how do you calculate the solder paste and stencil opening? So volume of solder paste volume is equal to V paste into 2 cross V fillet plus V PCB minus V pin into 2. So this is the formula which we need to consider, and the total volume is taken out by 2 cross common solder paste have to be considered the 50%, and stencil opening will be around what you call mm square V paste by stencil thickness. So this is the formulas which need to consider on this one. And then calculation of stencil opening. So diameter of the round opening is equal to 2 cross by stencil opening in mm square by pi, and slide square opening by stencil opening by mm square is given one side. So you need to consider divided by two sides. So if you are going for the square, you can have to go for the 4.3 mm square into 4.3 mm square, and if you are looking for the little bit wider one on the PCB, so if some customers may require extra solder pad, longer solder pad to have extra solder paste on the surface, so then we can go for 4.5 mm into 4.5. This is depending upon the how the vias has been designed, this one actually. So this is the formulas for calculating stencil opening. So it is about the formulas actually. Is one, if customer is facing any difficulty, if you are facing any difficulty, you can ask us. So we have already we can help you on this one, like stencil opening, how to calculate all these values with us. So if you took over this one for THR opening, so we have defined for circular pin, this is the values you need to consider, and for rectangle pin, for example, we have given a stencil calculation for this one. So you can contact us, we can help you on that, how do you calculation of stencil pin, and this will be helpful for the designing process. So now we have seen the emergence of THR, and we have seen that design consideration with respect of the product, and now we have seen that stencil calculations, how do you do it with the formulas and all those things. So now we will see the process control. What are the, how do THR process will be done, and what are the different stages we have in this one. The first thing is we can see in the screening that first thing is the screen printing, and then inspection, followed by the pick and place, manual placement, and reflow, and inspection and cleaning. So in screen printing, what we do exactly is we take the PCB, apply the solder paste, and then in inspection we see the dimensions, calculations, and alignment of the PCB as per which is suitable for the screen printing. And then we go for the pick and place, where the components will be picked by automatically from the packing and the place on the surface of the PCB. And next thing is the manual placements, where the components which cannot be placed automatically by pick and place, we manually place the components in the PTH, that is plated through hole. And once you assemble the components on the PCB will goes to the reflow oven, where the components get solder paste melts and components get assembled on the PCBs, and the PCB comes out of on the oven. And we do the inspection where the component has been properly soldered on the component on the PCBs, or PCB has component has been moved from the surface of the component. I mean solder paste which we designed, solder pad to be precise, moved out from the component has moved out from the solder pad, and that we do inspection. And then the cleaning, any residuals has been fallen, any flex has fallen, or any something has fallen on the PCB, that will be done by cleaning the PCBs. This is how the different process is going to happen in the what you call in the reflow process oven. And how does the status of the PCB and the soldering process? You can see in the picture, the first we'll take the PCB and this is the stencil and the PCB, position of the stencil. And the second picture tells about that how applying the solder paste. I mean, if you see this one, how many times we apply the solder paste on the PCB side and which angle we need to apply, that we'll discuss in the later part of slides. And once you apply the solder paste, fill the stencil hole. And if you see this product where the plated hole is been pin is been assembled on the wire, and then we did the reflow soldering. So once it is reflow soldering, the component solder in the PCBs. This is how the different stages of the PCB processes goes. And second thing is when you talk about the processing stages, and this one, the most important thing is the screen printing or paste printing. So this is very important. Screen printing, that means the first stage of the reflow soldering process. So where the screen printing stage will define how much solder paste volume is required on the surface of the PCBs. By defining, I mean, how much solder paste we define will define the quality of the soldering. So how the product is soldered on the PCB is after soldering, is the soldering is met the standards which we are talking about. And the solder paste which we are using on the surface of the PCB is a combination of flex and the metal also. So if you talk about the combination, the metal combination is more than 50%, sometimes 50 or more than 50%. We need to apply the solder paste twice so that there will not be any air bubble or any gaps will be there on the PTH, like we have pitted hole circuit. So that it has to be. And one more thing is, when we are applying solder paste on the PCB, you have to make sure that the angle of applying solder paste should be more or less 45 degrees, so that it takes proper filling of the PTH. And when we have done actually this one, we need to consider these 4 points, like choice of stencil thickness and the design, and the PCB designs and the connector layout, and the choice of the solder paste, and the speed and the pressure and angle of sequence used by the apply solder paste to the PCB. The first 2 points define the retain of how much solder paste should be retained on the surface of the PCB, and the last 2 points determines how well the solder paste is filled the PTH, and how well the component has been properly soldered on the in the PTH hole. So this is we need to consider this one. And one more thing we need to consider is the solder opening. So how do you calculate the solder paste? How much solder paste should be applied on the surface of the PCB will be determined by the 2 points. One is the thickness of the stencil and the opening of the vias, PCB holes. Normally in the market, when you talk about the stencil opening, it is like 100 to 200 micro ohms thickness we consider. And the via, solder opening is always depending upon the hole opening, always depends upon the PCB designers, how well they design actually. So if you look about this picture, so you can see there is 5 different THR processes, the hole openings are there. So if you talk about the first one is a typical THR openings of the openings of the THR. And if you look at the third thing, if customer wants more solder pad or more solder paste, then you have to go for the more solder pad. So that is where the third one defines. And then fourth one, if customer wants the bigger hole, then that has to be designed like this, so that has to be designed like this, so that when the solder paste, when you apply the solder paste, it should not fall from the bottom of the PCB. So that's the reason we advise to go for this kind of design. And the last one, if customer want to use the double-sided, like top and bottom, if you want to use the more solder paste, then this is the one which you can consider this one. So this is absolutely designer's choice, whenever the customer, what kind of customers their PCBs or how the THR process has to be done, and depending upon the component size which they are using. So then the second thing is the pick and place process. So the most important thing is once you've done that, and wherever it is possible, but we advise the pick and place process should be done automatically. So where the component can be picked from the package and placed on the surface of the PCB. But one thing is you have to remember is the pick and place process suitability defined depends upon the design of the connector, how well the connector, the size and the volume of the design connectors. Some of the THR components which we required normally use, there is a small change in the design, especially for example, if we look at into this one, the terminal block the vertical one, you have a cap on surface of the connectors. What happens is when nozzle will be used to suck the component from the package and the place. So during that process, this nozzle will suck the component only on the cap without touching the component with the air, and this places the component on the PCBs. But when you talk about the horizontal component, it will touch the body, because horizontal component will not have a privilege to have a cap on the surface of the top of the connector. So this is some of the designs. Normally we go for the pick and place machines. So once it is done, the packaging of the component also plays a very important role in the through hole process. So this is normally we go for the tape and reel packing. So where the SFD components or the THR components will be placed in the tape and reel, and this tape and reel will be given to the feeders in this one. And there the whatever the cap cover is there, it will be removed, and the component will be stuck from the cavity and the place on the surface of the PCBs. So when we are doing so, how much force we need to apply, that is also plays a very important role. So when it comes to the earth electronics, we normally go for the IEC standard, where the pulling force of the this cover has been defined to the 0.74 newtons, an average of 0.74 plus or minus 0.5, and the pulling weight is normally 75 grams, what we have defined this one over the cover tape. And the second thing is which direction. The moment if you take that this one, direction also plays very important. So that is also we will mention which direction you need to go with the feeder. So post and the limiting carriage, this is all defined in the data sheet of the particular components if you are using when it talks about the earth electronics. And the most important thing is the reflow oven necessary. So this is very, very important, how the component get assembled on this one. So what exactly the temperature. This is the graph. I just explained that what exactly happens, the solder profile of the any component. So if you see here, the moment you start the reflowing this one, the 30% of the temperature, there will be a sudden raise time will be very high, and it will reaches to the preheating area. So if you observe the graph, this one, the graph is divided into the three parts. That is the preheating area, this one, and ramp up temperature and the cooling. So most of the soldering process will happen in the preheating area. So where what exactly happens in the preheating area is, if you take about the PCBs, as I told in the beginning, it consists of different size of the components. So small, if you talk about the capacitors or inductors, which is very, very small, and if you talk about the connectors, which has very big pitch, depending upon 10.16 or 12 mm pitch also will be there. So the bigger volume product will require higher temperature to get the solder, and the smaller component will require the low temperature to get the solder on the PCBs. So we cannot define each temperature point for the different product. So what we talk about is a D-well temperature point. So what happens is we calculate and bring the one temperature point where all the component get sufficient type of heat so that they can get the components without affecting the component performance. That is called a D-well temperature point. And once it is done, then the temperature then will go to the next, where the temperature will be reach the maximum point. Normally we define the 265 degrees of temperature, but when it goes to the peak temperature, it will goes 20 degrees extra plus. Why? The reason is where the solder paste melts and it starts reflow, and where the component get assembled on this one. So when the solder paste melts, the surface tension come into the picture. So if you apply the proper, limited, how much solder paste required, then it will not affect the components, will not move out from the solder pad which we defined. So if we apply the more solder paste, then the solder paste melts, and because of the surface tension, the components moves away from the solder pads. That's the reason it is very, very important. We need to calculate the solder paste volume very perfectly, how much required. So once the component get assembled, then it will come down, and from the oven it is cooled down actually. So this every product, whatever I have explained, that raised temperature, fall temperature, peak temperature, everything is being defined on the data sheet of the every product. So you can see that depending upon the thickness of the PCBs which you are thinking, the values has been mentioned in the data sheet of when it comes to the Worth Electronics. So the last thing which I talked about is the quality. So how the quality is being mentioned. So when you talk about the quality, so we normally go for the IBC 6 and this one. So this is what we expect when you do the proper soldering on the PCB. The 100% solder paste should be filled, but practically it is not possible. But if you fill 75% of the solder paste gap, then it is sufficient to get the proper soldering. So this is how it looks once you in the X-ray machine of this one. So when you talk about the quality, quality has been done whether after soldering the component, whether the quality, the product has been done as per the quality or not. I have a few examples here. The first picture, you can see this one. This is not met as per the quality, because you can see on the left hand side the solder paste is properly filled, and the right hand side it is not properly filled. There is some gap is there. So this is not met the quality. And if you see right hand side, both the solder paste is been filled, but it is, we have given the more solder paste than what is required. So this is also not meeting the IPC quality, this one. And the second thing is, if you look at this picture, so you can see that only the one side the solder paste has been filled, other side is completely open. So this is not also meeting the as per the quality which we are talking about this one. And there is another picture. You can see that there is a air bubble has been created. Even the solder paste is one side is open, and the other side which is completely filled, that is also not done properly. You can see the air bubble clearly seen on the picture, so that we didn't get the proper quality look actually as per the IPC standard. So if you look at this one, this is a perfect solder paste we have done. There is how the quality has been met. It has met the IPC A61. This properly filled the vias, PTH holes, and assembled done properly. So this is quality wise, it looks perfectly. So this is how you need to check some of the points of the quality wise, and then the advantage of through-hole reflow. So we have seen the emergence of the through-hole reflow, and then we talk about the material change with respect to of the connectors which we use, and design change, and the calculation of stencils, how do you design, and then the process of the through-hole. So now we talk about the advantage. when you talk about the through hole, like how THD, the through hole component mechanically very stable, the same thing we can expect with the THR is also mechanically very strong, fulfills the THD through hole component, just like a THD component. And same thing, like the SMD through hole component can be reassembled with the reflow process. By doing so, you can reduce the process, and by doing then it ultimately leads the saving the cost. And as I told you that this saves the one production stop and saves the times and saves the money. So this is the advantage we have with the THR components. When you talk about the wood electronics, we have keep on adding whenever we are introducing any new product in our portfolio. We are keep on adding. Right now we have IO connectors, USBs, RJ45, and then we have terminal blocks, things which can in this we have a portfolio which can support the through hole reflow process components also. So now we will conclude like what kind of what we discussed, like when talk about the through hole reflow, dimension material housing has to be changed. That is why normally through hole component cannot be used without changing the enclosures. We have to change the materials and the something. And pins has to be shorter compared to the wave through hole component, which will be used for the wave soldering. Combines the advantage of SMD and the through hole. That is where one of the biggest advantage we have with THR process. Soldering in the reflow process and the manufacturing process also can be optimized because the SMD components, through hole components can be soldered with the reflow process. By doing so, we can save the time and money. So this is about the reflow, about the THR process. If you have any questions, we are open to that one. So with this, I conclude my presentation.
We can go now into the questions. When we can't answer all your questions in the live webinar now, we will answer them later on, or Vamsi will answer them later on via email. So then, Vamsi, let's just start with the first question. This one was regarding page 13, is 2.6 millimeter over PCB surface.
No, actually, it's not about the PCB. It's the total length of the connector. So when you assemble the connector on the PCB, it has to come out from the other side of the PCB. So normally, when I explain in the page 13, the PCB thickness for the THR process will be the 1.3 to 2.3. So when you assemble the connector on the PCB, the pin of the connector has to come out from the other side. So it's the total pin length, not about the PCB.
Okay. Vamsi, thank you very much. Okay, then let's go on with the next question. Is manually placement of a THR connector allowed?
Yes, because all the THR connectors does not have a pick and place placement possibility. See, some of the components you have to take it and place the connector on the PCBs. It is possible.
Okay, thank you very much. So then, there we have next question from Doreen. Can you please explain the calculation of the needed solder volume?
Okay, this I cannot give the overview. It depends upon the application, but as explained in my presentations, we have a formulas. So how do you calculate what is the solder paste length and stencil length on the PCB footprint? So this is how we need to calculate. But if you are using any worth component, you can directly come to us. We can give the calculations for the THR process.
Okay, thank you very much. So, Vamsi, if you want that we share the presentation, we can do that as well, but then we can just go on with the next question. So is there a rule of thumb for the drill size according to pin diameter?
It's no rule of thumb. So we have a formulas again, because again, it depends upon the application which you are working. So if you see in my presentations, I've shown the 4 to 5 varieties of PCB hole opening and solder paste. Some customers want just standard THR. If some customer wants to more extra solder paste to be done, then you need to calculate stencil pattern. And we have two more things. If customer wants double side of support, top and bottom, then that is calculations will be differ. So it is again how the customer wants, and the PCB thickness level also plays very important, and the stencil thickness. Normally, if you ask what is the thickness of the stencils, so depending upon the applications, the IoT applications or the industrial applications, the stencil thickness volume will differ. If you are working for the high power applications, normally we can calculate up to 200 microohms, but normally in the market it differ from 100 to 200 microohms. So I can say this: there is no thumb rule, but again, application wise, you need to calculate.
Okay, Vamsi, thank you very much for that answer. So then we just go on with the next question. Vamsi, can you explain the specialties of the USB-C THR pins?
Here I cannot explain because I need to have the pin connectors pins, and then based on that I can correlate whatever I have explanation. Can you please drop me the email? I can reply to email with respect to our component, and we do have calculations with respect to of type C USB connectors. I can help you through email.
Okay, thank you very much. So yeah, your question is also saved, so we can go through that just after the webinar in the next few days. So then maybe one of the last questions there, how can you compare the cost of THR components?
Yes, if you there will be a little bit higher side, because if you look about the components, it is little bit higher. But if you look at the overall process, I can say that the process and the component and the how do you assemble the component entirely process, this THR components are less price if you look at the complete process. But if you look about the only component, yes, as I told you that we'll be changing the design side and the material which we use. So not much, but overall cost wise it is less only, I can say.
Okay, Vamsi, thank you very much. Then I would say we go to the last question, and this is about, at the calculation, is there a difference for round pins and pins with 4 corners?
Yes, I think if you see my presentation in the PPTs, we have a different calculation based on the pin constructions. If you talk about the circular pin, the calculations will be WP by 2. And when you talk about the 4 corner pins, it is like square root of A minus B by pi. This is...
Okay. Vamsi, thank you very much for all the answers, and also thank you very much for the presentation. Yeah, then I would say also to all of you, thank you for your attention. Nice to have you here. I hope you enjoyed our webinar from our Digital We Days. And yeah, just stay tuned. There are a lot of more topics we will speak about in this week. And thank you very much and have a great day. Bye.